All right, so where we left off yesterday was the statement where f composed with g of x and g composed with f of x, if they simplify to be just equal to plain x, then that means that those two functions are inverses of one another. Okay, so that's what we're going to do here is verify that some functions are inverses of one another with algebra. There's another way we're going to verify too, but it's not algebraic. So, or what example we're on? F. Good. So f of x is 2x plus 3, and g of x is 1/2 parentheses x minus 3. Like that. So if we want to verify if these are inverses of one another, we need to do that function composition. Yeah, you do.
The way Joyner explained it.
Well, you have to verify it, and you're going to have to show me on the quiz the verification of it. It's like a it's like a proof, is what it is. So f composed with g, we did that last section, so that means we're taking g of x and replacing x with it. So you can distribute the 1/2 first, or you can distribute the 2 to the 1/2. I want to distribute the 2 to the 1/2 because it cancels out, so that I get x minus 3 plus 3, which is x. That's one direction. To prove it, you gotta do the other direction. We simplified this like you would when you do function composition. That if it equals x, that means that we think these are inverses of one another. To actually prove that they are, you've got to do both directions of the composition to prove that they are. So that's 1/2, and then we're going to replace x with 2x plus 3. I'm going to use a bracket.
Hey, you just switch them? Like you did F and G, and then you did G.
Yeah, G, F composed with G, and then you do it the other direction, G composed with F. To prove that two functions are inverses of one another, you have to show one direction and then show the other direction as well. Generally, if it works in one direction, it will work in the other direction. There are very few exceptions to that, but there are some. So you do have to show it in both directions. So here, that's going to be 1/2 times 2x, which is x. F x and g of x are inverses. That's what that proves to us, that we simplified those and you got that going on. All right. Let's do f of x is x cubed minus 27, and g of x is the cubed root of x minus 3. We want to verify whether or not these are inverses of one another. So just start with f composed with g of x. So that means we're taking the cube root part and putting it in the place of x. So that's the cube root of x minus 3 cubed minus 27. What happens when you cube a cube root? Gets rid of it. So it's just x minus 3 and then minus 27. Does that equal x? No, it equals x minus 30. F and g of x are not inverses. Yeah. If it fails one direction, that means it fails completely. It has to.
But then if it's right,
yes. If it's right when you do it the first direction, you got to turn around and do it the other direction.
It would always be just x.
Yes, if they're inverses, it will work out to be just plain x. If it's anything else, like here we got a plain x, but we also got minus 30. So that is anything different than plain x. They're not inverses of one another. Always going to be that way. So if it works out to be x, like Rain said, in the first direction, that means you need to turn around and do the other direction. If it turns out to be anything else, you don't have to do any more. Okay, so that's algebraic verification. All right. So the composition is algebraic verification. Don't have to worry about domain as much with this composition because you're just testing inverses. You're not trying to do domain and all that stuff of a composition. You're testing to see if they're inverses. The other verification is graphical. And this one, I mean, we're going to use the graphing calculator to do this. There's no point in graphing them all by hand. That's not going to really help us that much. So the what we're going to be looking for is inverse functions reflect across y equals x. Okay, which is actually not that hard to see. As long as everything kind of happens close to the origin, it's not real hard to see. But there's some key things that you look for when you try to verify it graphically. And let's look at an example of that. So let's verify graphically that f of x equals 2x plus 3 and g of x is 1/2 x minus parentheses x minus 3. Notice that's the same problems we did earlier. We verified algebraically that these two are inverses of one another. So when we look at this graphically, I want you to see what inverses of one another do graphically with reflection across that y equals x line. So on my graphing calculator, I'd go to y equals. I'm going to clear out anything else I've got. Make sure you got your stat plots turned off. None of those are darkened in because that'll screw up your graph. If you got them turned on, it may not even graph anything for you. And then you're graphing those equations, 2x plus 3, and then 1/2 parentheses x minus 3. And then I'm going to graph one other line. I'm going to graph the y equals x line so that I've got what it's supposed to reflect across in the picture as well. So my third one, I'm just going to make it y equals x. If you got the color one, this is where it's a little bit of advantage. You can kind of differentiate between the two. But we know that this one has a slope of 2, so it's going to be up and to the right. This one has a slope of 1/2, so it's going to be up and to the right, but a little more, not as steep. And then we know what that looks like too. So with the color one, you can say the blue one, the red one, and the black one. So here's the blue one. Here comes the 1/2 x minus 3. And then there's the y equals x line. The blue one is reflecting across that because it matches up down here. That's kind of like what you could think about is if I folded this screen across the black line, they would match up. Okay, where are they crossing at? But on what line? On the y equals x line. That's what they're going to do most of the time, cross on that line. If they don't cross at the same spot across the y equals x line, they're probably not inverses of one another. In fact, I'm sure that they're not. Because that one point right there, if you reflect it, it's the exact same point again. Because it's right there. They're all three hitting in the same spot. That is what that can look like. So let's look at another one that's maybe not as pretty. So, or maybe not as straightforward. So let me grab that screenshot and put that in our notes. These are inverses of one another. I'm not a big fan of graphical verification, but it is obviously faster than algebraic verification because you just have to graph them.
Wouldn't that be so close, like you couldn't tell on the graph?
Could be. Yeah, that's one of the drawbacks of the graphing, the verification by graphing. And the thing about it is, though, you can always do the algebraic. If they're asking you to verify graphically, you can still do the algebraic method with the composition because you've got the equations. If you're going to graph them, you got the equations anyway. So that sort of thing. The only time that it might be difficult to or impossible to do the algebraic is if they just gave you a graph and didn't tell you what the function that came from was. That's not going to happen often at all. Let's look at f of x and x cubed.
So with the question, things that we just go through, like,
Yeah, and I didn't mean to write f inverse. I meant to write g of x. So these are, they look very similar. They kind of look like opposites, inverses of one another. They may or may not be. If we want to verify this algebraically, we could do f composed with g and then g composed with f. If we want to do it graphically, let's see what that looks like. So to do that graphically, and the cubed root is the key here. It's the reason I want to do this because you may not know where to get the cubed root in your calculator or how to do that. So y equals, in y1, I'm going to put the x cubed minus 27. So x raised to the third minus 27. In y2, I'm going to put the cubed root of x plus 27. Now, a cubed root is also what exponent? 1/3 power. You could use that. So you could type it in as x plus 27 raised to the 1/3. And I put that in parentheses for really no apparent reason, but that's one way to do that.
You do it the other way.
You can do it with the cube root by pressing math, and then 4 is actually the cube root. 5 would be any other root, like a 4th root or a 5th root or something like that. And then you could do x plus 27 there.
how did you get
The cube root symbol comes from pressing the math button. And since it finishes, it's got to finish its thinking there for it. All right, so you press the math button, and then the fourth choice there on the first menu is where that is. If you need a 4th root, you can press the 5 button, and it'll put an empty box there, and you can type in whatever root you're dealing with. Not usually they don't get above cube roots in this section. We get into the chapter, or later in the chapter, we get bigger ones, and we'll talk about using that then. So, all right, so graphically, are those inverses? It's hard to see the whole graph. You don't see very much of the graph. It looks like you got 3 lines. I know that the cube or x cubed plus 27 is not a straight line, right? I know that the cube root of x plus 27 is not a straight line, but that's what it looks like when you get this little window shot of it. But look at where they're crossing. They're all 3 crossing on the y equals x line at the same spot. That right there is a good indicator that they are inverses of one another.
the blue dot looks like it's bending.
It is. They're all. If I press zoom out here, you'll see that they are very curved. The blue one, and then the red one is curved as well. And then the only straight one is the y equals x line. So there's the bigger picture of it. Normally, I mean, you're going to have your window set to the standard window 10 by 10, and you're not going to see everything. So it looks like they're straight. They're a little curved, but not much. But here they're curved quite a bit. But they still cross on the y equals x line. So if they cross on the y equals x line, it's a very, very good indicator that they are inverses of one another. Okay, so graphical verification. Not if they cross in the same spot. I can definitively say no. If they cross in the same spot, then they are definitely going to be inverses of one another.
But they could cross in different spots, right?
They could potentially, cross somewhere else or not cross at all. And that would indicate that they're not inverses of one another because they're not reflecting across that line. Okay, so F. So hierarchy of how inverses are verified, algebraic's the best way, no doubt. It's very dependent. You work out the math. If it equals X, they're inverses. If it equals anything else, they're not. Algebraic's the best way. Graphically, it's possible, but not the best of ways.
What if it equals like X squared?
Okay, you're probably going to have a domain part to that. So, like, that's a good question. So, like, say we have f of x is equal to x squared, and they tell us x is greater than or equal to 0. So, what part of that is the is the part of the parabola we're looking at? The right side of it. So that means this is a one-to-one function. So it could have an inverse. If it's not a one-to-one function, it can't have an inverse function. That's what we talked about yesterday. So if g of x maybe is square root of x for x is less than or equal to 0. Let's look at graphic notes. If we're verifying graphically. All right, so let's see. Here's how you could do that. X squared, and then parentheses. I'm going to hit X and then hit the second math, and then I'm going to get greater than or equal to 0. I want you to see how that graphs that. Well, it's yeah, I can use the restriction. See, it cancels out all the x's here and then just graphs that half of it, which is nice because that's the part I want. I think if I put a division symbol between them, it might even actually get rid of the flat blue line. I'm not 100% sure on that because I don't do this a whole lot. I usually just visualize it. I usually don't even graph them. Yeah. If you put a division symbol after your function, then the restriction of the domain, it'll graph just that part, which is nice. So we see that that's the part we're caring about for inverse purposes. And for g of x, it was the square root. So parentheses, the square root of x. Oops, not 2. What am I doing? X. Delete. Yes, yeah, and you won't have that on every one of them at all. And then this one was x is less than or equal to 0. So less than or equal to 0. So that would be second math, number 6 to get the less than or equal to, and then a 0, and then hit graph. Yikes. All right, so where's my graph at? Why is there no graph there? Very good. So can those be inverses of one another? No. Can we see graphically that it doesn't exist, so it's not there? Or doesn't exist in the real plane? So those are not inverses. Because the x's are less than 0. If I change that to greater than or equal to 0, we'll see a graph. Whoops. Delete, and then second math 4 0 parentheses. All right, so I changed that from what the original problem was. So there's the first one. Here's the red one. And then those would be inverses just by changing the inequality, changing nothing else. You've got to be careful about that with those particular pieces. The original problem here, g of x and f of x are not inverses. Graphically, they don't reflect across the y equals x line.
Would we only know that if you graph it?
No, you could do the composition and verify that as well. Anytime you have the equations, you can always do the composition and verify inverses. If you don't have the equations and they just say, here's a graph of two functions, are they inverses of one another? Think about, oh, if I fold it across y equals x, do they match up? Because that's the test for that. If you have the equations, I'm a algebra person. Let's do algebra. It's college algebra. That's the name of the course. So I'm a big fan of doing algebra to do it, to verify it. As you look at some of these on 415, 11 through 95, you'll see, you'll get the experience that you need to determine all that concept. Sure. Algebraically, you got to look at it and say, okay, well, the domains do matter this time. So if you did G composed with X, or F composed with G of X, we'll do that side first. Square root of X squared. You got to look at the domains because they do matter on this because they gave you restrictions. Okay, so here we had the original problem was that, and that's the one that's not inverses or another. These are imaginary, right? So when you square imaginary numbers, you get what back? Negative numbers, right? What are those? Positive numbers, not negative numbers. So because of the domain, algebraically, yes, that's going to show you that it equals x. But what kind of x is it based on the domains? It's negative numbers. The original one had positive only. So that restriction throws it out. So this is a very rare exception that algebraically it shows x, but we have to think about the domains on that. That's not gonna be the case very often at all. And if you did it the other direction, it's also going to give you x, but you still got to think about the domains and how it doesn't work.
So if you see that the one domain is less than x and one is greater than, do you have to do working out that correctly? If you see the domains are like that.
I would, because it's not necessarily true that these just happen to be, it's the correct equation for the inverse, but the domain's wrong. That's why you would need to check it anyway, because the domain could be the right domain to make it work. So you would need to check it algebraically. Trust me, you'll do these problems on this page, you'll get the experience you need to do these. I can't do a problem like every problem you will see because I'd be here for 45 days doing problems. If you'll do these practice problems, you'll get the experience you need to be able to recognize that stuff. That was an exceptional problem in the fact that it had the right equation but the wrong domain to make it work. And so that's a rarity.
Hey, can I pause this back?
Yeah.